Some pretty famous science has been done during pandemics. For example, Isaac Newton is said to have discovered that gravity is a universal force during a quarantine period. Well, another scientist who did some really interesting work, part of it during a time when he was quarantined, was Galileo. Some of Galileo's most famous experiments involve a ball and a ramp. In fact, right here is Galileo's actual ball. Don't believe me? Look, it's got his signature. Okay, I'm just joking. It's actually the core out of an old softball. But Galileo would roll a ball down a ramp because he wanted to study how things fall, but things fall too fast for him to see. And he didn't have cameras back then where he could slow the motion down. So he slowed the motion down by rolling the ball down ramps. So let's see one of Galileo's famous experiments. Now here I have a notebook, but I'm going to use that as my ramp. And I'm going to roll this ball down this ramp, and let's see how far it goes. So I'm going to let it go right at the top, and it went, what, 3 inches? Let's try it again. Maybe a couple inches more, but it doesn't go very far. Now you might say to yourself, well, of course it didn't go very far. You're rolling it on grass, and grass is really rough. It's also wet this morning. Well, let's see what happens if we put our ball on a little bit less rough surface. So I'm on a sidewalk now. Got my ramp set up. Let's put our ball on the ramp and observe. The ball definitely goes farther. Hits an obstacle and actually bounces back. But that's obviously more than a few inches. This ball that I was calling Galileo's ball, relatively smooth. Let's see what happens if I swap it out for a ball with a rougher surface. So we'll try a tennis ball. It's not quite the same size in circumference, but it is roughly the same mass. Let's see what happens. I'll place the tennis ball on the ramp and release. Now obviously we should repeat that experiment several times, but it did not go as far as the smoother ball. The smooth ball went approximately 9 feet. This ball went less than 7. Now let's see what happens when we roll it inside on a smooth floor. It didn't go very far. I'll repeat that experiment just so you can see it wasn't a trick. Now let's try the smoother ball. It's about 30 feet. I tried it on a couple of other surfaces. On this rough surface it went about 6 feet, and on this hallway it went about 19 feet. But you can see there are clearly a lot of bumps in the road. So what can we conclude from these experiments? Well, first, if the ball is rough, or if the ground is rough, then the ball does not move very far. However, if the ball and the floor are both smooth, the ball rolls a long way, although it does eventually come to a stop. Now, our ball did have some rough spots on it, and the floor also was rather bumpy. What would happen if we could make both of them perfectly smooth? And what would happen if we could make the ball perfectly round and the floor perfectly flat? Galileo concluded that if you could somehow make perfectly smooth surfaces, perfectly flat floor, perfectly round ball, so that gravity and no other forces were present, that the ball would simply move at a constant speed in a straight line forever. In other words, no push or pull would be required to keep it moving once it was set in motion. And it is not actually part of the ball's nature to somehow come to a stop, contrary to what you might think just from observing how things move in everyday life. Galileo thought of a different set of experiments that brought him to the same conclusion. He said, if you set two ramps in front of each other, and then you place a ball on one ramp and let go, that ball will roll up the other ramp to very nearly the height that it initially was on the first ramp. In fact, the balls will keep rolling back and forth, nearly reaching the same height on either ramp, only losing a little bit of ground each time. Now, this is the really ingenious part of Galileo's thought experiment. What if you lower the right-hand ramp? Well, the ball rolls a further distance, but it goes up to very nearly the initial height. If you lower the second ramp even more, again, the ball rolls further and further and further, always reaching very nearly the initial height that it started at. But what if you lowered the second ramp all the way to the floor? In other words, you took the second ramp away altogether. Then what would happen to the ball? The ball would keep trying to seek its initial height, but it could never reach it because there is no incline for it to roll up. So Galileo reasoned that if the ball is perfectly smooth and round, and if the floor is perfectly smooth and horizontal or flat, then gravity would not be a factor. There would be no other forces at work, and so the ball would simply continue to move in a straight line at a constant speed forever. In everyday life, we observe that if a ball starts moving, it also comes to a stop. But what Galileo was saying is it does not come to a stop of its own accord. It is not the nature of something to simply come to a stop. It is forced to come to a stop because it is colliding with the things that it is moving past. Contrary to your everyday observations, it is not the nature of something to stop moving, but to keep moving. It is natural for every material object to resist changes to its state of motion. This discovery by Galileo that everything resists changes to its state of motion is now called inertia. Inertia is a property of all objects, and therefore it is something that we need to take into account in our study of motion. And so we will be looking more closely at this property of inertia.